Welcome to another lesson of thermodynamics. Today we're going to talk about phase change. You've probably heard of solids, liquids, and gases before, but let's take a deep dive into their physical properties first. For example, in solids, the molecules or atoms just vibrate in place. They're really closely packed together, and the forces that bind them are strong. In contrast, in gases, the molecules or atoms just bounce all over the place. They're really spaced apart, and there's almost no force that binds them. Liquids are somewhere in the middle. They flow around, but they're bound by gravity to stay close to each other. There is also some force that binds them together. In addition, solids have a definite volume and a definite shape. Liquids also have a definite volume, but they take the shape of a container. Gases are just really flexible. They expand and contract at will, and they also have the shape of the container. Now let's talk about phase changes. Well, pretty much everyone knows the phase changes between melting and freezing, along with condensation and evaporation. But let's talk about the transitions between solids and gases. Sublimation is the phase change between solids and gas, and deposition is the name for the transition from gas to solid. These two transitions happen because it might happen too fast for a liquid to form, like how frost will form from the water vapor in the air, or it can also happen when the liquid just cannot form. For example, carbon dioxide will sublimate and deposit. Think about it. Why do some things, like water, actually have a liquid state, while others, like carbon dioxide, cannot become liquid? Well, technically, carbon dioxide actually can become liquid. In fact, what phase a material is doesn't just depend on temperature. Pressure, which is how much something is compressed, matters too. When the pressure gets low enough, and this pressure will vary between materials, the material will sublimate. For example, for water, it is at 611 pascals, or 1/166 of atmospheric pressure, which means that water can become a liquid. For carbon dioxide, this threshold is actually greater than atmospheric pressure, and carbon dioxide sublimates as a result. Solids, liquids, and gases aren't the only three phases either. In fact, when something is heated and pressurized above a critical point, it can become a supercritical fluid. These supercritical fluids share physical properties with both liquids and gases, and it behaves like something between a liquid and a gas. I did an experiment regarding the boiling of water. In this beaker, I have 50 milliliters of water and there's a thermometer that dangles into it. Below them, there is a burner, and it will heat up the water for around 20 to 30 minutes. In the next slide, I'll give you the data that I measured from the beaker and the water in it. What you may find might surprise you. Well, for the first 5 to 10 minutes, the water actually heats up rapidly, from 25 to 75 degrees Celsius. Well, you might think, this experiment is really easy. You just go up to, it's just going to go up to 100, evaporate really fast, and now you're going to have no water in your beaker. Well, actually, do you really think that a boiling point of water is exactly 100 degrees? Well, actually, water can actually boil below 100 degrees. And here's why. What I observed was that at around a 10-minute mark, the heating actually became slower and some of the water started boiling. Eventually, the temperature leveled out at 88 degrees, 12 degrees short of the 100-degree mark. And the water continued boiling. Well, what's actually happening here is that the water that's escaping is the hottest water, the water that has the most energy. It might be around 100 degrees. However, the temperature that I measured was around the average temperature of the beaker. Even though most of the water was still at 88 degrees, some of the water had already reached 100 and was leaving the surface and evaporating. This also explains why the temperature or the heating process became slower. This is actually because since the hottest molecules were escaping, the average decreases because there is less of the higher average. And as a result, the average temperature will decrease and the heating efficiency will actually slow down. And in the first 10 minutes, the water gained 25 degrees Celsius. In the last 10, it gained around a quarter of that. Isn't that surprising? Thank you for watching.